Phenols will react with sodium hydroxide and they will form sodium phenoxide ONA plus H2O, and I told you this is water soluble. And your phenol is water insoluble. Insoluble in water. Okay. And also I told you this will not react with sodium bicarbonate. NaHCO3. If you treat with phenol with sodium bicarbonate, no reaction. That means this is a weak base. And this is a strong base. So a strong base is required to remove this proton. Weak base is not sufficient to remove that proton. Okay, this is an important reaction to distinguish between carboxylic acid. This is how you can distinguish between a phenol and a carboxylic acid. Carboxylic acid. So this is how you can distinguish between a carboxylic acid and phenol. Okay. Now, why phenol is acidic? That we have already described. See here, this phenoxide anion can be stabilized by resonance. Why phenol is acidic? Phenol is acidic. The reason is anion, resulting phenoxide anion, resulting phenoxide anion is stabilized by resonance. Stabilized by resonance. You have to draw the resonance structure as an answer. Don't forget that. You know how to draw the resonance structure. You know very well how to draw the resonance structure of phenoxide anion. We have done it before in the class. So resonate this. Draw resonance structures. Okay. So phenol is more acidic than alcohols. So phenol is more acidic. It is more acidic than alcohols. Say for example, C2H5OH. Okay. If you put sodium hydroxide, this will dissociate into C2H5O minus plus H plus H3O plus. Now this is not stabilized. This is not stabilized. You can see that. CCH3, CH2O minus. Now look at the inductive effect of this CH3 group. It will polarize the electron towards the oxygen. So it is the inductive effect is destabilizing. Inductive effect. Inductive effect increases electron density on the oxygen. On the oxygen. What does it mean? It is localizing the negative charge. It is not delocalizing the negative charge. Localizing the negative charge. Not delocalizing negative charge. Okay, localizing the negative charge, it is increasing the electron density and hence it is less acidic. Hence, less acidic than phenol. It is less acidic than phenol. Right. So that is the acidity and basicity of phenols and phenoxide anion. Okay. Now let us look at the reactions of phenols and phenoxide anions. Reactions of before that, again we have to talk a little more about acidity. Suppose you introduce one second. Yeah, two more people are coming. Sorry, I didn't notice this. Still more are there. One second. Okay. Yeah. Now, let us look at the acidity of phenols a little more. What we can do is we can take what is the effect of different substituents. Let us look in this way. Suppose we have compounds like this, see here. See this. I have phenol. Then I have phenol with CH3 group here. OH with NO2 group here. With NO2 group here. Now which is more acidic? Which or arrange in the order of decreasing acidity. Arrange in the order of decreasing acidity. Okay. So most acidic 1, 2, 3. So acidity decreases acidity. Decreasing acidity. This is how you have to arrange. And then explain or give reason. What will you do? How will you do that? What you have to do is you just write OH plus H2O giving O minus. Okay, we'll put an R here. That is important. Okay, now stability of this anion. stability of this anion. Stability of this anion increases acidity. That is a criteria. Increases acidity. Okay. Now, compare these three. OCH3 is electron. OCH3. Electron withdrawing or electron donating? Electron donating. It is electron donating. So what it will do? What it will do? OCH3 will donate electron to the benzene ring. And what is the effect? The effect is, see, electron is flowing in this direction. What is the effect? Localization of charge. The effect is localization of negative charge. How does it affect the acidity? Decrease of acidity. Okay, please draw the resonance. Remember, resonance is very, very important in all your answers. Now draw NO2 group here. Plus and minus. Draw NO2 group. Again, you generate the O minus. See this? All details, all the lone pair, everything you have to draw. All the lone pairs. Now what you have to do? See here. This is enough. Even one structure is sufficient. See this. And this. Okay. So you can draw this resonance structure in this fashion. See here. N, O minus, O minus, N with a positive. Here, double bond, O. Okay. So, delocalization of charge. Delocalization of charge. And hence, increased acidity. So, which is the most acidic one? This is the most acidic, number 1. This is less acidic than this, and this is 3. So, here is 1, 2, 3. Which is 1? Nitrophenol. Methoxyphenol is the least acidic. Nitrophenol is the most acidic. Okay. So, this is about the acidity of phenols and effect of substituents. This is what is called effect of substituents on the acidity of phenol, right? So if you have electron withdrawing groups, electron withdrawing groups, electron withdrawing groups, EWG, electron withdrawing groups will increase acidity. Will increase acidity. While electron donating group decreases. This is what you have to remember. And I have already taught you how to find out whether a group is electron donating or electron withdrawing. That we have already discussed. Okay. Now let us see some of the reactions of phenols. Okay. Suppose we take, Suppose I take this a general phenolic compound, NO2 and OH. See here, NO2 group is electron withdrawing. This will be very acidic. And now you take this with CH3, CH2, CH2, CH2Br. You take in presence of potassium carbonate, K2CO3 and acetone. What will be the product? What will be the product? Say this is actually a two-step reaction. What are the two steps? This will react with potassium carbonate first, K2CO3. K2CO3 is a base, and this is an acid. And you will get, see this, O minus and K plus. A stabilized nucleophile. Remember, you have generated a nucleophile. Okay. Now in the second step, this will react with 1, 2, 3, 4 and Br, N-butyl bromide. Okay. Now we have studied this reaction. This we have studied. See here, 1 H is here, 1 H is here. So here is a primary alkyl halide and here is a good nucleophile. See this. What mechanism? Primary alkyl halide. It will undergo SN2 mechanism, substitution reaction by SN2. So what is your product? I got NO2 and O, CH2, 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 CH3. This is the product. Okay. So this is, these are very common reactions. Methoxylation, that is ether formation. So this is a method of forming ethers from alcohols. Okay, so this is an ether. Nitro ether, I'll say. Nitro ether, nitro ether. Okay. Now you can do many aromatic reactions using this aromatic electrophilic substitution reactions with this aromatic, which we have already studied. Aromatic electrophilic substitution reactions. We have studied this before. If you take phenol, we will just treat with 1 second, just one. Now we have, see here, phenol. Yeah, you just take bromine and water. See, phenol is highly electron donating. OH group is highly electron donating. What is the consequence? The electron density of the benzene ring is increased. Hence, what happens? The substitution is very, very easy. Oh my God, some people are coming and knowing it. Oh, sorry. I will just keep it here. Okay, okay. I'm not knowing that you people are coming. One second, one second. Nora. Yeah, very sorry. I was now. So bromine reacts and it's so electron donating. It is so electron donating that all the three auto and para positions are brominated. So you get tribromophenol. You get tribromophenol. Okay. So this is bromination, and it is very difficult to control this reaction. Remember that. Very difficult to control. And you have other electrophilic substitutions. Other electrophilic substitutions, you should never nitrate this. That also I have told you before. Using nitric acid, HNO3, H2SO4, it explodes. Okay, it is very, very dangerous reaction. I have told you in the class about what happened in our lab. Okay, so this is electrophilic substitution level. Let us look at other reactions, most important, some of the very important reactions of phenol. It is this one, oxidation of phenol. This is a very important reaction. If you take phenol and oxidize it with potassium dichromate, K2Cr2O7, in presence of sulfuric acid, dilute sulfuric acid, you can use, you will get what is called as quinone, an interesting compound. Look at this. This is called quinone. Okay. Because they have got oxidation reduction. These are very interesting compounds which has got oxidation reduction properties. Compounds with oxidation reduction properties. You are going to come across many of these type of reactions. Now, what is the oxidation reduction property? It can transfer. You can keep. You can reduce this. You can if you treat this with any reducing agent like SnCl2. If you treat this with any reducing agent, this will undergo reduction to form OH OH. This is called a hydroquinone. Hydroquinone. And you can convert this hydroquinone back to quinone or benzoquinone. This is benzoquinone. Or quinone. Got as quinone or benzoquinone. Now this you can convert this back by oxidation with Na2Cr2O7. Na2Cr2O7 sodium dichromate. Clear? So these are the important reactions of phenols. So that is phenols. Now let us look at an important compound of phenol. which we are very much familiar, that is phenolphthalein. Let us look at phenolphthalein. Phenolphthalein, you know what it is. What is a universal indicator for acid-base reactions? So indicator in acid-base indicator. The working principle, everything we have studied before. We have not looked into the structural at that time. Okay, let us see what is the structure of phenolphthalein and how is phenolphthalein prepared. Now, look at the name. Look at the name phenolphthalein. You have two portions. One is phenol, and then you have phthalein. Now, phenol is having this structure, and phthalate is phthalic anhydride. Phthalic anhydride. Now, this is phthalic acid anhydride. See here. This is phthalic anhydride. So, if you take two molecules of phenol and one molecule of phthalic anhydride and react in presence of sulfuric acid, a very interesting compound will form. You see, you have two molecules. Okay, an electrophilic substitution will occur actually. It is an electrophilic substitution occurring, and this para position will attack this. See here. Look at what happens. So it forms an anion here. This anion comes and attacks you. And this gets opened up. Right? So what will you get as the product? Let us see. Let us see what you will get as the product. Somebody is there. One second. What happened? This one second. Oh yeah. I hope you can see my board. Can you see the board? Are you able to see the board? Kanao? Okay. That is what I am trying to locate. The sharing is gone. That's it. Yeah. Now, can you see now? Okay, okay. Now let's see this reaction. So we have phenol. It is forming the bond here. We have to be very careful on writing this. So you have what is this? Yeah. I have to write my and COO minus and oxygen. Okay. So I have used only one molecule now, OH. Now this can still undergo one more attack. See here, a second molecule, OH. I will make it this way. I will just I'll make you understand with all the double bonds and all input. See here how the reaction occurs. Now see, yeah, see that. So the para position, this para position is forming a bond here again. And what do you get? What do you get? You get OH, then this ring, then a second phenolic group. OH, okay. And then you have the benzene ring. Right? Now, uh, this, this one second. You have the OH here and COO minus. Okay. Now, what happens is this will replace this OH group and will give you your phenolphthalein, and this is phenolphthalein. OCO. See this. This is the structure of phenolphthalein. So this is OH ether. Phenolphthalein. Now, please write these steps and study this. It is not very difficult. It is only an electrophilic substitution reaction. This is nothing but aromatic electrophilic substitution reaction. Aromatic electrophilic substitution reaction. This is the nucleophile. The benzene ring. The electron-rich benzene ring is a nucleophile. This is the CO group. It attacks the CO group. This is just like a Friedel-Crafts reaction. It's very similar to a Friedel-Crafts reaction, but you are doing it 2 times. So try to write this mechanism and learn it. Don't try to follow this mechanism. Don't simply by heart the whole stuff. Try to follow this mechanism. Okay. See the last step. Attack of CO minus again on this carbon to remove the OH. So step by step you study this mechanism, and that will be a very good exercise. So what is your starting material? Thallic anhydride. Don't forget the starting material. Phenol, 2 molecules of phenol and thallic anhydride. This is thallic anhydride. Thallic anhydride. Okay. And uses of phenolphthalein, all this stuff you know. Okay. Now, so this is about phenolphthalein. Now let us look at next class of compounds, that is ethers.